Hello everyone and welcome to TalentSprint. In this session we are going to discuss about circles, which is a very important and interesting chapter from geometry. So let's start with the definition of a circle. Now I'm sure you all know what a circle is, right? Or how a circle looks like, right? See, if you observe, circle is nothing but a collection of points, right? It is a collection of points and all these points are equidistant from a given point, which is known as the center of the circle, right? Let's say here the center of the circle is O. Now if I collect all the points which are equidistant from this point O and connect them, then what we get is a circle, and it looks like this, right? So a locus of all those points which are equidistant from a given point forms a circle. Alright. Now we need not discuss about the area, perimeter, etc. here, because that's a part of mensuration which we have already covered in that topic. Here we'll be looking at various parts of a circle and the important properties of circle which are helpful in answering questions from this topic in various exams, especially in the SSC exams. Alright. So this is a circle with center O. Now you know that a circle has some radius, right? Radius is nothing but the distance from the center of the circle to the circumference, right? So here let's say the radius is r. It is generally denoted by small r, right? So distance from center of the circle to the circumference of the circle is called the radius, right? And this whole length is called diameter, right? Anyway, we'll look at diameter at later point. But so this is about a circle, right? A circle with center O and radius is r. Now this boundary here, as you all know, is known as circumference, right? What is the circumference? Circumference or the perimeter, right? It is 2 pi r. Right, circumference of a circle is equal to 2 pi r, where pi is a constant, right? 22/7. So 2 pi r gives you the circumference, where r is the radius. Now you know that diameter of a circle, right? Diameter of a circle is twice the radius. It can be taken as 2 times the radius, right? So if you want to take circumference in terms of diameter, you can take it as pi d, right? See, 2 pi r is the circumference. We know that 2 into r is the diameter, so this becomes pi into d. All right. And area of a circle. What is area of a circle? It is pi r square, right? Pi again is the constant there, r is the radius. So area of a circle is given as pi r square, or again, if this has to be taken in terms of diameter, we can take it as pi d square by 4, right? Because r is equal to d by 2, so d by 2 whole square, which gives you d square by 4. So area of a circle can be taken as pi r square or pi d square by 4. So these are the basic measurements there, right? The perimeter, or which is specifically called as circumference in this case of circle, and area, right? 2 pi r and pi r square respectively. Well, this is a part of mensuration, right? Here we are going to look at the geometry of circle, which means the various properties of circle. So that's the basic introduction. Now let us look at important parts of a circle, and then we'll look at various properties related to those parts, right? So I would like to start with something called as arc, right? All of you would have heard about an arc, right? What is an arc? Arc is a part of the circumference of the circle, right? You know that this is a complete circumference, right? This complete boundary is called as circumference. Now some part of that circumference is called as an arc, right? Arc. So what's the definition? Arc is, you know, some part of the circumference, right? For example, let's say from A to B, right? A to B. This is called arc, right? This is called as arc. Now always you'll have two arcs. One is a major arc, the other is a minor arc. Now if you look at this part, this is minor arc, right? The smaller one. And the other part, AB, right? AB can be seen in two different ways here. From A to B when you go clockwise, or from A to B when you go anti-clockwise. So what you see anti-clockwise here is the major arc. So this is called the major arc. Right? This is called the major arc, right? Minor arc and major arc, right? So arc, as you all know, is the part of circumference, some part of circumference. Now how do you measure the length of an arc? See, now that, like I said, there are two ways to look at it. You can either call it a minor arc or major arc based on what you are considering, right? So how do you measure the length of an arc? Whichever it is, whether it is minor or major, how do you get the length of it, right? So let's see how do you measure this length of an arc. See, it is very simple. Based on the concept of proportionality, you can find out the length of an arc. We know that the total angle in a circle, is 360 degrees, right? Now, the complete circumference is with respect to 360 degrees. Are you able to follow? The circumference 2 pi r is for 360 degrees. So I can say if the angle is 360 degrees, you understand? You know, total angle is 360. And understand, any arc would make an angle theta at the center. Any arc will make an angle theta at the center. So if you look at this minor arc, let's say, when you try to connect A and B with the center of the circle, it makes an angle theta. The complete angle is 360, but the angle subtended by that arc at the center of the circle is theta. Now based on this proportionality between theta and 360, you can find out the length of the arc. So I can say the complete angle 360 degrees corresponds to 2 pi r, right? The complete angle in a circle 360 degrees gives you the circumference 2 pi r. But what we need to consider now, only this angle theta, right? If I take the complete angle, we get 2 pi r. So theta gives you what? Theta gives you what? This is nothing but the length of the arc. Now simply by cross multiplication you get the required answer there, right? So the length of the arc can be taken as, see, theta into 2 pi r divided by 360, or theta by 360 degrees into 2 pi r, right? So basically this is how you measure the length of the arc. Alright. Now if you want to measure the length of minor arc, you can say theta by 360 into 2 pi r. If you want to measure the length of major arc, then what is this angle? See, the complete angle is 360. The angle in the minor arc is theta. So what will be the angle in the major arc? It will be 360 minus theta. So there you can take it as 360 minus theta by 360 into 2 pi r. So basically the concept is arc is some part of circumference. So total angle 360 gives you 2 pi r. Whatever angle is subtended by the arc at the center will give you the length of that arc, right? Whether it is major or minor. So that's about arc, right? So simple, that arc subtends some angle, certain angle at the center. Based on that angle, we can find out the length. Now, the next important part of a circle which we need to learn here is sector. What you have learned so far is arc, and like I've mentioned, arc is a part of circumference. What is a sector? Sector is a part of the complete circle. What you have seen so far is arc, which was a part of circumference. But sector now is a part of the complete circle, right? Now this complete area is pi r square, as we have discussed, right? Complete area is pi r square. Now some part of that area which is enclosed between two radii is called as sector, right? For example, we can consider the same sector here, right? For example, this shaded region, what I'm shading now is the sector. It can be referred as a sector, right? Some sector of a circle. That's like a pi. Out of a complete circle, you have removed one pi. So how do you measure the area of that sector? With respect to arc, we take the length. With respect to sector, it is area, because sector, like I've mentioned, is a part of the complete area. Arc is a part of the complete circumference. Circumference is nothing but length. So sector, how do you measure the area of a sector, right? Area in a sector. How do you get area in a sector? See, same concept. With respect to the complete angle 360 degrees, for the total angle 360 degrees, the area of the circle is pi r square. With respect to theta, how much will be the area? Same proportionality concept, cross multiply and you will get the required area there, right? So the area of a sector can be taken as the angle subtended by the sector or the arc of that sector at the center, which is theta, divided by 360 degrees into the area of the complete circle. What is area of complete circle? Pi r square. Pi r square. So this is the area of a sector. Alright, so both are kind of related. An arc forms an angle, subtends an angle at the center, which gives you the length of the arc. When you take the complete portion there, right? This is radius. See, O2A is radius, O2B is also radius, right? This is radius, this also is radius. So the region between two radii is called sector. And how do you get the area of that sector? Angle subtended at the center, theta, divided by 360 degrees, the total angle, into the complete area pi r square. So these are some important parts of a circle, the arc and sector. Now there is one more component which is called as segment, right? What do you mean by segment? Segment of a circle. See, let's consider another arc, right? For example, let's say if I take xy, this portion x and y, right? Let's say it subtends an angle alpha here at the center, right? So you know that xy is an arc, right? Xy is an arc, and this shaded region will give you the sector, right? Sector xy. But we are now looking at segment. What is meant by segment? See, segment is the complete sector minus the triangle formed by the arc. See, x, y, o. X and Y are the points on the arc, right? X and Y are the 2 points of the arc. O is the center of the circle, right? So if you see X, O, Y makes a triangle. Now from this complete sector, right? From the complete sector, when we subtract the triangle, what we get is known as segment. So this portion here, this shaded region here is known as segment, right? This is called segment. You understand? This is sector like you have seen, right? But segment is a part of the sector. Right? Anyway, all these detailed definitions and explanations of all these terms is not required, but then some basic idea is always good, right? So segment is some part of the sector. What part of the sector? From the complete sector, if you subtract the triangle, what the remaining part you get there is called as sector, is called as segment, right? So if I have to measure the area of a segment, how do we get area of a segment? Area of the sector minus area of the triangle. Alright, area of the sector minus area of the triangle. Even in the first sector there is a segment, right? This is called segment. I didn't take it because it will become too clumsy there, but this is the segment, right? The shading that I'm doing now is called segment. However, let's take this segment so that it is easy to understand, easy to follow, right? So how do we get the area of the segment there? Area of the sector minus area of triangle. Alright, so for that segment, if I have to calculate the area, I can take it as area of sector minus area of the triangle. What triangle? XOY, area of the triangle XOY. Now we all know how to measure the area of sector, right? Area of sector has the already taken here, theta by 360 into pi r square. So what is area of this sector? See, the angle subtended at the center has been taken as alpha. So alpha by 360 into pi r square. This is area of sector. Minus area of the triangle XOY. What is the area of the triangle XOY? See, if you go by sine rule, area of this triangle can be taken as half r square sine alpha. See, this is radius again, from O to X, O to Y. Any point, right? Any point on the circumference when connected to the center of the circle gives you the radius. So these are the radiuses there. The angle at the center is alpha. So area of a triangle, you know, can be taken as half r square sine alpha in this case. So minus half r square sine alpha. Anyway, like I said, all this formulae and all are not required, right? These are part of mensuration, so we need not worry about this. But then comes the properties, right? Various properties of triangles based on chord in a triangle, right? Chord, secants, tangents of a triangle. So mostly we see that questions from geometry are based on chords and tangents, right? Not on area, sector, segments, etc. But then, like I said, having some basic idea about all these things is good, right? So we have learned the basic concept of a circle, right? The basic definition and some parts of circle. So the first one is arc. We have two portions there, major arc and minor arc, right? And the length of the arc is in proportion to the angle subtended at the center. Alright, it can be taken as theta by 360 into 2 pi r. Then there is something called as sector. Sector is the part of area of the circle, which again is proportional to the angle subtended at the center, right, by that arc. Then segment. Segment is minus the triangle formed by that arc there. Alright, which can be taken as alpha by 360 into pi r square, which is nothing but sector area, right? Sector area minus half r square sine alpha. For this segment, if I have to find out the area, you understand, this complete is sector. Don't get confused. This complete is sector. This portion is called segment. So for the top segment, if I have to find out the area, how will we get that? See, area of the sector, which we have taken as theta by 360 into pi r square, because the angle at the center is theta. So theta by 360 into pi r square minus area of this triangle. What is the area of the triangle? Half r square sine theta. Alright, so that's how simple it is. Alright. So the next point that we are going to look at is about the chord of a circle, right? So let's understand what is meant by a chord. I'm sure all of you have heard about this term chord, right? A chord is a straight line joining any 2 points on the circumference of a circle, right? A straight line joining any 2 points on the circumference of a circle is called a chord. For example, let's say here we have a circle with the center O, right? Now a straight line joining any 2 points. For example, you take 2 points on the circumference. Let's say this is point A and here is point B, right? So this line joining A and B is called chord. Alright, so that straight line AB is called as the chord of the circle. Now there are infinite chords in a circle because we can, take any 2 points on the circumference and connect them to get a chord. Alright, so AB is like a chord. Likewise, let's say you connect these 2 points, right? This is X and this is Y. So XY is another chord, right? XY can be taken as another chord. The largest chord in a circle is the one that passes through the center of the circle, right? Any chord that passes through the center of the circle is the largest chord, which is nothing but the diameter of the circle, right? For example, if you connect, let's say these 2 points, right? Let's say this is X, X dash. So X, X dash becomes the diameter of the circle, which is the largest chord, right? Anyway, so the discussion here is about chord. So 2 chords we can see here. AB is one of them. X, Y is the other chord. Now let us look at some important properties related to chords, right? I'm sure all of you have got the definition right. 2 points on the circumference when connected through a straight line gives you a chord. Now, the first important point that we need to understand is when a perpendicular is dropped from the center of the circle to a chord, it will bisect the chord. Now what do you mean by bisecting the chord? It will divide it into two equal halves, right? We have already learned what is meant by bisecting a line, right? Bisect means to break into two equal halves. So when we draw a perpendicular, when we drop a perpendicular from the center on any chord of that circle, it will bisect that, right? For example, this is the center here, right? So if you try to drop a perpendicular, right? So this is the perpendicular there, right? 90 degrees angle. So we will find that if it, let's say if it meets at point AC, it meets the chord at point C, AC will be equal to CB, right? AC will be equal to CB. Likewise, from the center again, if I try to drop a perpendicular on this chord XY, right? So it will be like this, let's say, right? This is 90 degrees, all right? So you'll find that if this point, let's say, is Z, so XZ will be equal to ZY, right? So any perpendicular dropped from center of a circle on any of the chords will bisect that chord, right? So here we'll see that AC will be equal to CB and XZ will be equal to ZY, right? This is based on the concept that perpendicular drop from center will bisect the chord. Or the converse is also true, right? One way to look at it is that whenever you drop a perpendicular from the center on any chord, it will bisect the chord. Or if you say that you will draw a line such that it bisects the chord, you will draw a line from the center such that it bisects the chord, then it will be perpendicular to the chord, right? The converse is also true, right? So both the ways we can take it. Drop a perpendicular from the center on the chord, it bisects it. Or drop a line from the center on the chord such that it bisects the chord, then that line will be at right angle to the given chord. So that's the first point here, right? I'll just mention it here so that you can follow it easily. A perpendicular dropped from the center of the circle on any chord will bisect the chord, right? So that's the point that I'm referring to, right? And converse is also true, like I've mentioned there. So that's something which you need to make a note of. So just make a note of this point, then we'll take up the next one. So any perpendicular from the center to a chord will bisect that chord. So that is one important point I would say, right? These are all like small theorems, right, which you need to remember. It's like a theorem which you need to remember, right? Application of this we'll see while solving the questions, right? All these small points that we discuss, all these properties that we discuss will help us solve the question. So you must be very strong in the properties of circles there or any sort of geometrical shape there, okay? Now let us look at the next point. The next point here is about equidistant chords. What we have learned now is about dropping a perpendicular from the center, but the next point is about equidistant chords. Understand, if two chords are equidistant from the center, then they are equal, right? For example, from the center to this chord there is some distance. Let's say the distance is D. Now on the same distance, if I draw another chord, let's say on the opposite side, right? Or let's not take it as D. D is generally diameter. Let's say the distance is A here, right? Or I'll better take another circle so that you don't get confused. Okay, let's say in a circle you have from the center you have two chords which are equidistant from the center, right? So if I take the distance D, right, and draw a chord here, and on the same distance D if I draw a chord on the other side, right? Let's say this is AB and this is A dash B dash. Then what is the important point here? AB will be equal to A dash B dash. This is the center of the circle. Get the point? So if two chords are equidistant from the center, right, this length is D and this length also is D, right? So if two chords are equidistant from the center of the circle, then they are equal. So here I can say AB is equal to A dash B dash. AB is equal to A dash. And here again the converse is true, right? Instead of saying that when two chords are equidistant from the center, they are equal, I can say that two equal chords are equidistant from the center, right? Two equal chords are equidistant from the center. So the converse also is true. Now let's just make a note of this point as well, right? Two equal chords. Equal chords, when you say equal in length, right? Obviously equal in length. So two equal chords are always equidistant from the center of the circle. Right, are equidistant from the center of the circle, right? And it need not be kind of parallel chords, right? The chord can be any way, right? For example, I can say this chord, let's say this is another chord, A double dash, B double dash. So the distance of this chord is also D, right? If this distance is also D, then we can say AB equals to A dash, B dash is equal to A double dash, B double dash. You're getting the point? It need not be that the chords are always on the opposite sides or always parallel, right? That need not be the case. And like I mentioned, the converse is also true. So either the chords are equal. If the chords are equal in length, then they are equidistant from the center. Or if two chords are equidistant from the center, then they are equal in length. So that's the second property with respect to chords. Alright. Let's look at the next point. The third point. Third point or the third property. Now the third property here is about two intersecting chords. Alright. Let's look at the third property, which is about two intersecting chords. If two chords of a circle intersect at a point internally or externally, then there is a very important property which can be observed. So let me just explain this to you with the help of a diagram, right? So let's say there is a circle and here we have got the center O. Now there are two chords, right? This is let's say AB is one chord and CD is the other chord. CD is the other chord, and they intersect internally at a point E. At a point E, right? Or there may be a case where the two chords they are extended and they intersect at some external point E, right? Even in that case, we'll find that AE into EB will be equal to CE into ED. Very, very important point, right? I mean, you just need to remember these things. We have no idea on when it will be useful, right? It can come in use any time while solving the questions, right? So it can be either internally or externally, like I've mentioned, right? So let's say there's a chord AB. This is AB chord, right? You have extended this. Then there is a chord CD. You have extended this as well, right? This is CD. Both of them come and meet at an external point, right? The chord is AB. The chord is AB and the chord is CD here, because we cannot say AE is the chord. Chord is always within the circle, right? You cannot call AE as the chord, but then you're extending the two chords so that they meet at an external point, right? It is not compulsory that always the chords will intersect internally, right? They can either intersect internally or externally. But in both the cases, we'll see that AE into EB, even in this case, AE into EB will be equal to CE into ED. Alright, so whether the chords intersect internally or externally, we can find this to be always true, right? This always holds true. So AE into EB, which is from one point of the chord to the meeting point, the length, into EB from the other point to the meeting point end, right? So the product of those two lengths for both the chords will be equal. Now the last point or the last property of a chord here is with respect to intersecting circles. Now let's say two circles intersect each other, right? Here I'm talking about the next point of chords. When two circles intersect each other, right? Intersect each other. It's obvious that when two circles intersect each other, there will be two intersection points, right? So there can be a common chord, right? So this property or this point is with respect to such a common chord. So let's say there are two circles, right? Equal or unequal, but they intersect each other. So you see these A and B are the two intersecting points. Let's say the center of the first circle is O, the center of the second circle is O dash. Alright, and we see that the two circles intersect, right? So when they intersect, there will be 2 points of intersection. A and B are those 2 points. Now if you observe, when we connect AB here, it is a common chord. This chord is common for both the circles, right? AB is on the, A and B are the points on the circumference of the first circle and also on the circumference of the second circle. And by definition of chord, we know that 2 points on the circumference when connected gives you a chord. So AB is a common chord. Here A and AB will become a common chord for both the circles here, right? Both the circles C and C1, C and C dash, let's say, right? With centers O and O dash respectively. So the point to be noted here is, in such a case, this common chord will always be perpendicular to the line joining the two centers. So if I join the two centers here, right, this will be perpendicular. The angle here made will be 90 degrees, right? So in such a case, the common chord AB will be perpendicular to the line joining the centers. Alright, so that's the fourth point about chords. Alright, so in any common chord, you see that it will be perpendicular to the line joining the two centers. Now both the circles need not be equal, right? I've already mentioned this, right? One can be of smaller radius, the other can have a larger radius. But obvious that when two circles intersect, they'll always have two intersection points, and those 2 points can be connected to get a common chord, and such a common chord will be perpendicular to the line joining the two centers, right? Irrespective of the size of the two circles, right? Irrespective of the radius of the two circles there. So that's the fourth point. So before we move on, let us understand a very important point with respect to chords or arc in a circle, right? Let me just explain this to you. This is a very, very important property, and it will be helpful in answering many questions based on circles here. Now we have already learned what is meant by an arc, right? An arc is some part of the circumference. So let's say AB is an arc here. AB is an arc, and we know that this arc, again when we look at AB as an arc, there is another arc in the anti-clockwise direction which is AB again, right? So minor arc and major arc. The point to be noted here is, let's say the angle subtended by this arc AB at the center is theta, right? This angle is theta, right? This is the center of the circle. O is the center of the circle. O is the center of the circle, right? So the angle subtended by the arc AB at the center is theta. Now if you look at the major arc, see, this is minor arc. If you observe, this is minor arc, and this part here is a major arc. The other arc is called major arc. So always it is divided into two arcs, minor and major. Now this same arc AB will also subtend some angle at any point on the major arc, right? So let's take some point here. Let's say at the center it has subtended an angle theta. Let's say at this point it subtends some angle, and this angle will always be half of the angle subtended at the center. And not just at this point, right? You take any point on the major arc, the angle subtended by AB will be half of the angle subtended at the center. For example, if I take this point, so the angle subtended by AB at that point, right? This is theta by 2. This is theta by 2. Or you take any point here, right? So the angle subtended by A and B, right? This also is going to be theta by 2. So clearly any minor arc can subtend two angles. One angle at the center, the other angle on some point on the major arc, right? Always the angle subtended at the center, theta, we can say is double of the angle subtended at the major arc. Major arc or the other arc. Same goes with the major arc as well. For example, if you consider this circle, right? Look at AB or A dash and B dash, right? Now let's consider the major arc, right? This is the major arc. It subtends some angle at the center. This time I'll take this angle. See, angle subtended at the center is this by the major arc. This time we are considering the major arc. Earlier we have looked at the minor arc theta. Now we are looking at the major arc. So this major arc, this complete arc, major arc here, right? See, the challenge is both major arc and minor arc are A dash, B dash. So it may sound a little confusing, but understand, this time we are referring to the major arc. So this major arc has subtended some angle at the center. Let's say this is alpha or theta, right? Even theta would be okay. Two different cases. This is the center of the circle O, the angle subtended is theta. So the same major arc will also subtend some angle at on the minor arc, right? So you take this angle, right? Or you take any angle. This angle will be theta by 2, right? Or you take any point. For example, if I consider this point, this angle will be theta by 2, right? Any point on the minor arc, the angle subtended will be half of the angle subtended at the center of the circle. Okay, so this is a very, very important property. We will see that we use this in many questions that we solve from circles. All right, and if you now look at it, it is also applicable for a chord, right? A and B, when you look at as an arc, it is arc. But if I connect these 2 points, it becomes a chord. So the angle subtended by the chord at the center and the angle subtended by the chord on the other part of the circle, there is a relationship. What is the relationship? The angle subtended at the center is always double the angle subtended on the other arc, right? So I hope all of you have followed this important concept here. All right. Here again, A dash B dash can be considered as a chord. So this chord A dash B dash had subtended. Now this time, if you look at A dash B dash as a chord, this is the angle. You understand? This angle. So this angle is theta. The angle subtended on the other part of the circle will be half of theta, right? So that's an important concept, right, with respect to arcs as well as chords there. Fine. So I'll just give you a note here. Angle subtended by I'll say minor arc. or major arc, right, at the center is twice the angle subtended Understand? The angle subtended by minor arc at the center is twice the angle subtended at the major arc. Any point on the major arc, right? Subtended at any point. Right? Any point you consider it is always twice the angle subtended at that point. And the angle subtended by major arc at the center is twice the angle subtended at any point on the minor arc. Are you able to follow? So this is a very important property. And I'm sure you are also aware of the fact that if it is a semicircle you know is like half of the circumference, right? In that case the angle subtended at any point on the other half is 90 degrees, right? If you take a circle, let's say, right? Now this is like AB. AB is actually the diameter, right, passing through the center of the circle. Now this is an arc. This is semi-circumference. You understand? The complete is circumference. This is semi-circumference. Now this time the arc is complete. It is making a semicircle. Now the angle subtended by this arc at any point on the other arc. The point here is this time both major and minor are equal. In case of a semicircle, major arc is equal to minor arc, right? So anyway, if you take this arc, the angle subtended by this arc at any point of the circle, at any point on the other arc is always 90 degrees. We have learned this concept while discussing triangles, right, in the topic of triangles. So if you take any point, let's say this point P, the angle subtended at P by AB will be 90 degrees. You take this point, the angle subtended, let's say this is P dash, this will be 90 degrees. Or you take some other point, let's say P double dash, the angle subtended at this will be 90 degrees. Same goes when you take the other half of it, right? This is also the semicircle. So the angle subtended by this semicircle at any point on the other arc will be 90 degrees, right? So two important points here. One is that, and if you observe, the angle subtended by the semicircle at the center is how much? 180 degrees. So again here also it satisfies, right? The semicircle at the center the angle is 180 degrees. At the other arc the angle is 90 degrees. So satisfied, right? We have always seen that any arc you take, the angle subtended at the center is twice the angle subtended in the other arc at any point in the other arc, right? So both the ways it is correct. Alright. So that's about a very important point from circles, right, related to arcs. Let us now discuss about tangent of a circle. Now I'm sure all of you know what a tangent is, right? A tangent is a line that touches the circle exactly at one point on its circumference, right? Any line which touches the circle only at one point on the circumference is called a tangent. And there's another type of line which is called secant, right? What is secant? Secant is a line which intersects the circumference of the circle at 2 points, which cuts the circle at 2 points. So such a line is called a tangent. All right. So I'm sure you are clear with the point, and this is a very popular term, in fact, right? A line that touches the circle exactly at one point, right? Is a tangent. Alright. Then there's something called a secant. Let's also look at what a secant is, because there is some property of tangent correlated with secant as well, right? What is a secant? A line that cuts Alright, see, these basic definitions are not required. If you understand the concept, more than enough. You need not learn the definition by heart there, right? So a tangent, like I've mentioned, is a line that touches the circle exactly at one point, right? Any point on its circumference, but it should touch only at one point. Such a line is called tangent. And a secant is a line that cuts the circumference of a circle at 2 points, right? So if you look at the basic representation of tangent and secant with the help of a diagram, it is as follows. Let's say this is a circle, right, with center O. Now what is a tangent? A tangent that touches the circumference at any one point, right? And there are infinite tangents. How can we say there are infinite tangents? See, a circle is made up of infinite points, and at every point we can have a tangent, right? At each point on a circle we have a tangent. So infinite points, infinite tangents, right? So this is a tangent. It touches only at one point, right? This point. This is called as the point of contact or point of tangency, right? The point at which the tangent touches the circumference is called the point of contact, or it is also referred as point of tangency. So if this is the point P from which we have drawn a tangent, this is the point of contact T, let's say, right? And what is meant by secant? Secant is a line that cuts the circle at 2 points, right? So if you say this is P dash, it is cutting the circle at 2 points A and B. So PAB is called a secant, right? This is a secant, and this is a tangent. Again, secants are also infinite, right? You can draw infinite lines cutting the circle at 2 points, right? But remember, tangent always is touching only at one point, right? And you have infinite tangents. So this can be taken as one tangent, right? At this point, this is, let's say, T double dash, right? So this is also a tangent. So tangent is the line that touches the circle at one point. Secant is the one that cuts the circle at 2 points. Let us now look at properties associated with tangent and secant, right? Now, the first and a very important property with respect to tangent is that the angle made by a tangent at the point of contact with the radius through that point of contact is always 90 degrees, right? For example, if I take a circle, right, this is the center of the circle, and let's draw a tangent, right? Let's say this is the tangent. This is the point of contact T, and this is the tangent. So PT is the tangent there. Now from the center, when you try to draw a radius through that point of contact, right? So if you try to draw a radius here, it will form an angle of 90 degrees, right? So the angle made by the radius at the point of contact with the tangent is always 90 degrees. A very, very important property with respect to tangents, right? So the angle between the tangent and the radius of the circle through the point of contact, right? To the point of contact, to the point of contact or point of tangency, right, is 90 degrees. Very, very important, right? Now if you take any other point, it will not be 90 degrees, only at the point of contact. And of course, tangent and this radius can be connected only at that point. You know that tangent touches the circle only at one point. Here it may look like, there are 2-3 points of contact, but actually always it touches only one point, right? When you're drawing, because it is thick, it touches, but otherwise it connects only at one point. So at that point of contact, the angle made by the radius and the tangent is always 90 degrees. Just make a note of this, and like I said, this is a very important point with respect to the tangent of a circle. Okay. Looks like there's some discussion going on. Now let me give you the next point, right? Next point is about length of a tangent, right? So let's look at this. Now let's say if we draw two tangents from an external point, right? From an external point, if I draw two tangents to a circle, right, then the length of both those tangents would be equal. So let's say this is the circle and the center is O here. From this external point P, I'll draw two tangents. One towards the top, there is the point of contact, let's say this is A, and the other towards the bottom of the circle, right? It is the point. I'm just struggling to get a straight line there. This is the point B. Alright, so these are tangents. PA is one tangent, PB is the other tangent, right? From one point, you see that it touches the circle only at one point here, A, and here at the point B. Alright, so the point to be noted is this PA will be equal to PB, right? PA will be equal to PB. So what's the point here? The two tangents that we get from one external point on a circle will be equal, right? The length of both the tangents drawn from an external point on the circle is equal. So PA will be equal to PB. And by the way, how do you measure the length of a tangent? See, it is like this. Let's say the distance between the center and the point, external point P, is D. This distance here is D, let's say. Right, the distance between the center and the external point P is D. Now we know that from the center, or you know, the radius and the tangent makes an angle of 90 degrees at the point of contact. So this angle is 90 degrees. Likewise, this angle here is 90 degrees. This is the radius R, and this also is the radius R. Okay. Now if you really look at it, we have got two right angle triangles. OAP is one right angle triangle, OBP is the other right angle triangle, because here we have the right angle 90 degrees, here also we have the right angle 90 degrees. So the point is OAP and OBP are right angled triangles. Right, OAP and OBP are both right angle triangles. And you know what property or what theorem holds true in a right angle triangle, right? The Pythagoras theorem, very, very important, right? So by the application of Pythagoras theorem, we'll be able to find out the length of the tangent PA or PB. Of course, both of them are going to be equal. We have already discussed that. PA will be equal to BB. But how do we get that length? See, this is a right angle triangle. So PA is the base, OA is the perpendicular, PO will become the hypotenuse, right? PO is the hypotenuse. Are you able to follow? So if I take one of them, right, in triangle, let's say in the triangle OAP, right, what do you see? This is what is formed there, right angle. Right angle at what point? At the point of contact, which is T. This is the center O, and this is the point P, right? Now we know that OP is equal to D. We have already considered this length as D, and OA, the point of contact is A. OA is the radius R. So by the application of Pythagoras theorem, can we find out what is PA? Yes. What will be PA? Root over D squared minus R squared. Yes or no? We know that AP square plus AO square will be equal to PO square. Pythagoras theorem, right? What is AP square? AP square is what we need to calculate. AO is R, so R square, and PO is D, so D square. So AP square equals to AP square plus R square equals to D square. AP square is equals to D square minus R square. AP will be root over D square minus R square. So the length of the tangent can be taken as square root of D square minus R square, where D is the distance from the center of the circle to the point of, to the external point from where you have drawn the tangent, and R of course is the radius of the circle, and both PA and PB are equal. So we can say PA equals to PB, which is equal to root over D squared minus R square. So this is how we can always measure the length of the tangent, when you know the distance from the center of the circle to the point from where you have drawn the tangent. Alright, so D is the distance and R is the radius of the circle. This is about length of the tangent. So two important properties we have discussed so far. One is that the angle made by the radius at the point of contact with the tangent is 90 degrees. The second property here is about the length of the tangent. Let's move on to the next property here. So let us now quickly discuss about a few more properties with respect to tangents, the number of tangents, right? Direct common tangents, direct transfer tangents, and then we'll look at examples. So let's look at another property based on tangent and a secant, right? Now let's say there is a circle with center O. Now from an external point P, right, you have drawn a tangent and a secant for the same circle, right? So let's draw a tangent. Let's say it is PT, the point of contact is T, and let's also draw a secant, right? Now secant, you know, is a line that cuts the circle at 2 points, right? So PAB becomes the secant. We have already discussed about the definitions here. Now the point to be noted is, in such a case, PT square, PT is what? The length of the tangent, right? From the external point P to the point of contact. PT is the length of the tangent. So PT square will be equal to PA into PB, right? Very important. This again is a property based on tangents and secants and can be helpful while answering some questions. So the point to be noted here is PT square will be equal to PA into PB. And this also brings us to another important conclusion. Let's say if I draw another secant from the point P, right? If I draw this secant, this is cutting the circle at C and D. Now PT square should be equal to PC into PD, right? So I can say PT squared will be equal to PC into PD. And by combining these two, we can conclude that PA into PB equals to PC into PB. You understand? So there are 2 points that we can learn here. One is that from an external point, when we draw a tangent and a secant, then the length of the tangent square will be equal to PA into PB, where A and B are the points at which the secant line cuts the circle. And the other point is, from an external point, when you draw two secants, right? One is PAB, the other secant is PCD. In that case, PA into PB will be equal to PC into PD. PA into PB will be equal to PC into PD. Alright? So this is one property which is a combination of both tangents as well as secants. Alright? So let's look at pairs of circles. So here we are going to look at two circles, right? Now various important points here, right? For example, let's say when there are two circles which touch each other externally, right? Two circles are touching each other externally, a pair of circles which touches each other externally. Now both the circles can be same or can be different. I mean, can be of same radius or of different radius. So when they touch each other externally, right? This is the point of contact. Now let's say the radius here is this is the center O, the radius is R, and this is O dash, the radius is R, and this is a point of contact P, right? This point is P here. So the important point which you need to understand here is the point of contact lies on the line joining the centers of the circle, right? Whenever two circles touch each other externally, right? Whenever two circles touch each other externally, that point of contact between the two circles is on the same straight line which is connecting the two circles, right? Now maybe here, because we have drawn two circles just one beside the other, it's okay, but you take in any way. For example, here is a circle, the other circle is here, this is the other one, right? Now you see the point of contact is P. Let's say this is O dash and this is O. So when you connect the two centers, you'll find that the point of contact P lies on the line which joins the two circles. This looks to be a improper center, right? So if you look at it now, O and O dash is the line joining the two centers, and the point of contact P always lies on the line joining the two centers. Alright, so just remember that the point of contact is collinear with O dash, right? Or we can say O, P and O dash, all these 3 points are collinear, which means they lie on a same straight line. Now let us understand what are the different types of tangents that we get in case of a pair of circles, right? When we have a pair of circles, what are the tangents that we have? So let's consider an example where we have two circles which are not touching each other, right? Which are at a distance from each other. So this is circle 1, and here we have the circle 2, right? So in a given pair of circles, we'll have two types of tangents. One is called a direct tangent, the other is called a transverse tangent or a cross tangent. So let's define these circles first. This is a circle with center O, here is a circle with center O dash. Alright. Now there is a common tangent possible for both the circles, right? Both the circles can have a common tangent, a direct common tangent, right? And there will be two such tangents possible. First of all, two types of tangents. One is a common tangent and the other is a transverse tangent, or you can call it a cross tangent, right? So direct tangent is like this, right? These two circles have a direct tangent. Let me just write. Okay, and there's another direct tangent here. Right, so let's say this is A, B, and this like A dash, B dash. So A, B and A dash, B dash are direct tangents. These are called as common direct tangents, right? Common to both the circles, and these are direct. Now the other category here is transverse tangents, right? Or cross tangents. What are cross tangents? Which are, you know, not straight. I mean, these are like cross. So there will be two cross tangents possible, right? You understand the point? So these are called as cross tangents, right? These two are cross tangents. And these are called direct tangent. This is the direct tangent. This also is the direct tangent. Alright, so that's about the types of tangents that we have in case of a pair of circles, right? So when we have two circles, and now let us look at, let's say the radius here is R1, this radius is R1, and the radius of the second circle is R2, or let's say R and R dash, the radius are R and R dash respectively. And the distance between the centers, right? If you connect O to O dash, let's say from the two centers, the line joining the two centers is of length D, right? This length is D, let's say. The radius are R and R dash respectively. Alright. So how do we measure the length of these tangents? Understand, direct tangent or direct common tangent. These are formulae, you just need to remember, right? Direct common tangent length will be equal to root over D squared minus of R minus R dash whole square. Right, this is the length of direct tangent. And the length of transverse tangent will be equal to root over D square minus of R plus R dash whole square. Get you the point? So two types. So when the two circles are not touching each other, right, when they are distant at a distance from each other, we'll have two direct common tangents and two transverse tangents. Length of those tangents will be given as root over D square minus of R minus R dash square for common tangent, direct tangent, and for transfer tangent it is root over D square minus of R plus R dash whole square, where R and R dash are the radii of the two circles respectively, and D is the distance between the centers of the two circles. Alright, so important formulae, just remember and apply them to get the required answer, right? For example, the radii are given and the distance between the circles is given. He'll ask you to find out the length of transverse tangent or the length of the direct tangent. Just substitute in the right formula. See, the point to be noted here is direct tangent will be longer than a transverse tangent, right? Because see, from in this direct tangent we are subtracting D square minus of R minus R dash. This is a smaller value. Here we are subtracting a larger value. You understand? So it is clear that direct tangents are longer than transverse tangents. Just make a note of this. Alright, again maybe this doesn't look appropriate. I mean, it is touching at point E here. Let's say this is point F. This is, it will not touch at the same point, right? B and the two tangents will touch at different points, because at each point we can have only one tangent. So don't misunderstand that both B and E or this transverse tangent and direct tangent will be at a common point. It's not that, right? So EF is one tangent, and let's say CD is the other tangent here, right? C, and this is D. So the common tangents are AB and A dash B dash, the direct tangents, right? And the cross tangents are, what do we see here? EF and CD. CD and I think Ajay says, I don't think pairs of circles is important for SSC tier. Well, sometimes we see that we get questions on this. I mean, we cannot just neglect pairs of circles. It is important that you learn all this formulae. See, the challenge is this, right? Geometry is a vast subject, right? It is like, it is not a part of mathematics. It's like a subject on its own, right? And you never know what kind of questions would be asked. So that is the reason I'm trying to cover all the properties. We'll look at a few examples, right? But I'm sure if you follow these properties properly, then you should be able to solve the questions without any difficulty. We can say direct common tangents and transverse common tangents, right? These are also common tangents only. You understand? Common to both the circles. This transverse tangent is common to both the circles. This transverse tangent is common to both the circles. The direct tangent AB is common to both the circles. A dash B dash is also common to both the circles. So both are like common tangents, but two types: direct tangents and transverse tangents. So again I can say common uses like transverse common tangent or common transverse tangent, whichever way you call it. The formula are important. You should know when it is direct how to measure, and when it is transverse, when it is cross, how do we measure. Alright. Now there may be a case where the two circles are touching each other externally. In that case what happens? Like the previous point that we discussed was when the two circles touch each other externally. So the point to be noted is when two circles touch each other externally, the distance between the two centers will be the sum of the radius. Yes or no? Let's look at that. Now that we have learned about the types of tangents, let's look at the different cases possible. So when the two circles are disjoint, when they are not touching each other, two direct tangents and two transverse tangents. What happens when they touch each other? Right? What happens when the circles touch each other? See, understand. For example, this is one circle and here is the other circle, right? So this is the center O, here is the center O dash, right? Now if you look at it, this is radius R dash, this is radius R. So I can say D in this case is equal to R plus R dash. Yes or no? The radius of the first circle is R, the radius of the second circle is R dash. The distance between the two circles is nothing but R plus R dash. If you really look at this, there will be two direct tangents. Yes or no? This is one direct tangent, this is the other direct tangent. But will there be a cross tangent? Will there be a transfer tangent? No. Are you able to follow? Do you see a transverse tangent here? Because what will be the length? Substitute D equals to R plus R dash. If you have to find out the length of transverse tangent, this is R plus R dash whole square minus of R plus R dash whole square becomes 0. Right? So the point is there will be two direct tangents. Now what happens when so there will be two direct tangents? There won't be any cross tangent as such, right? There won't be any cross tangent. Get the point? We don't have. See, this is common to both the circles. This is also common to both the circles, but so two direct tangents, but transfer tangent is not possible. What happens when the two circles are touching each other internally? In that case, what do you see? For example, let's say this is a bigger circle and there's another smaller circle here. Right? Touches each other. So, this is the center and here is the other center. Let's say this is O, this is R dash, and this is center O. This length is R. This is O dash. So for the smaller circle, the center is O, the radius is R dash. For the larger circle, the center is O and the radius is R. Right? Now in this case again what happens? The distance between the two centers. What will be the distance between the two centers? See, this is complete R dash, this is complete R minus R dash. You understand? I've shown it that side so that you don't get confused, otherwise this is completely R and this part is R. So the distance between the two centers is D. Right? How do you measure D in this case? D can be taken as modulus of, or we can say D is equal to R minus R dash. D is equal to R minus R dash. When the circles touch each other internally, right? When the two circles touch each other internally. R minus R dash. The distance is R minus R dash. Alright. Now when the distance is R minus R dash, do you get direct tangents? No, because this is D, R minus R dash whole square minus of R minus R dash whole square. This becomes 0. Right? We'll have one tangent here, right? One cross tangent we can say, right? And when the two circles are congruent, right? When the two circles have the same center, in that case there won't be any direct tangent or any transverse tangent, right? For example, this is a larger circle, center O. With the same center, we have another circle. Right? So this radius is R, or let's say this is R dash, and this is R. Right? Now there cannot be a common tangent in this case, right? Because a tangent has to touch a circle only at one point. Now if that tangent touches this circle, it won't be able to touch this one. Right? Likewise, if a tangent is touching this circle, it won't be able to touch the circumference of the external circle there, right? So in such a case, when the two circles have got the same center, there won't be any common tangent, right? So in a case of pairs of circles, we have two types of common tangents, direct tangents and transverse or cross tangents. The length of the direct tangent is given as root over d square minus of R minus R dash whole square, and that of transfer tangents is given as root over d square minus of R plus R dash whole square. That's it. Radii will be given to you, the distance will be given to you, you just have to find out the length, substitute in the formula and get the required answer. So that's about all the different types of properties related to circles and arcs and chords. secants, tangents, etc. So what is a cyclic quadrilateral? A quadrilateral where all the four vertices lie on the circumference of a circle is called a cyclic quadrilateral. And the property that we are going to look at now is that the sum of opposite angles in a cyclic quadrilateral is always 180 degrees. And we can prove this using one of the simple points that we have discussed in the introduction part of this topic, right, which is based on circles. So what do we do? Let's consider a simple circle first, right? So let's say this is the circle, and let us draw a quadrilateral here, right? Quadrilateral such that all the four vertices are on the circle, circumference of the circle. So let me take the vertices this way so that it is a little easier to explain. Alright, so let's say A, B, C, D, right? A, B, C, D is a quadrilateral, cyclic quadrilateral here, right? Why? Because A, B, C, D, all the four vertices are on the circumference of the circle here. Now let's say the center of the circle is O. The center of the circle is O. Now if you really look at it, BD is an arc, right? BD is an arc. This is the minor arc and the other one is a major arc, right? Minor arc and major arc. Now let's say the angle subtended by the arc BD at the center is theta. So I'll just try to draw this. This is center O anyway, right? This is center O. The angle subtended here is theta, or let's say theta 1, right? The angle subtended by the arc BD at the center is theta 1. Now we know that if this is theta 1, angle A will be theta 1 by 2, because for BD, the minor arc BD, center is this O, and the alternate arc, the major arc, in any point on that major arc, you know that angle made will be theta 1 by 2. Yes or no? We have learned this point, that the angle made by an arc at the center is twice the angle made by the arc at any point on the alternate arc. So if this is minor arc, or any point on the major arc, A is a point on the major arc, so this is theta 1 by 2. Likewise, if you look at the major arc BD now, right, the major arc BD, let's say the angle made at the center is theta 2. The angle made at the center is theta 2, right? For this major arc, the angle made at the center, theta 2. If this is theta 2, what will be angle C? Theta 2 by 2, half of that angle. Same argument again, right? The major arc BD, if you go from B to D in the clockwise direction, that's the major arc. That major arc makes an angle theta 2 at the center. And at any point on the alternate segment, let's say the point is C, the angle made will be half of this angle. So half of theta 2. Now if you look at it, this is a complete angle theta 1 plus theta 2. So I can say theta 1 plus theta 2 is equal to 360 degrees. This is the angle in a circle is 360 degrees. Theta 1 plus theta 2 is 360 degrees, right? Now if you look at angle A, what is angle A? It is theta 1 by 2. How about angle C? Angle C is also, angle C is theta 2 by 2. Let's add the two angles, angle A plus angle C. Angle A plus angle C will be equal to theta 1 by 2 plus theta 2 by 2. We already learned that theta 1 plus theta 2 is equal to 360. So this is 360 degrees upon 2, which comes out to be 180 degrees. So I can say that angle A plus angle C is equal to 180 degrees. And A and C, as you know, are opposite angles. If A plus C is 180, it is obvious that B plus D will also be 180, because the sum of angles in a quadrilateral is always 360 degrees, right? The sum of all the angles should be 360 degrees. So angle A plus angle B plus angle C plus angle D has to be 360 degrees, out of which we know that A and C is 180. So B and D will also be 180. So I can say angle B plus angle C is equal to 180 degrees. So from these 2 points here, B plus C equals to 180 and A plus C equals to 180. What do we conclude? We can conclude that the sum of opposite angles A and C and the other pair of opposite angles B and D will be equal to 180 degrees. So clearly in any cyclic quadrilateral, the sum of opposite angles is 180 degrees. And obviously in any quadrilateral, the sum of all the four interior angles is 360 degrees. We have used that point as well here. And like you see, this property here is based on the angle subtended by the arc at the center is twice the angle at any point on the alternate arc, right? Based on that property only we have proved it. So I thought it is important that we cover it here itself. Actually this is the part of quadrilaterals, right? So which anyway we will discuss, right? All the different types of quadrilaterals like squares, rhombus, parallelogram, rectangle, trapezium. There we also look at something called a cyclic quadrilateral. So that's about the different properties which are related to circles and its parts like tangent, chord, etc. Let us now discuss different examples.